Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In the depths of space where gravity reigns supreme, black holes have long been considered the ultimate cosmic vacuum cleaners, objects so dense that nothing, not even light itself, can escape their gravitational embrace. For decades, this understanding formed the bedrock of our knowledge about these mysterious celestial phenomena. Yet in 1974, a young physicist named Stephen Hawking would challenge this fundamental assumption and revolutionize our understanding of the universe's most enigmatic objects. The story begins with Albert Einstein's general theory of relativity, published in 1915, which predicted the existence of regions in space-time where gravity becomes so intense that it creates an inescapable boundary, the event horizon. Beyond this point, classical physics suggested that all matter and energy would be trapped forever, destined to fall toward the central singularity where the laws of physics as we know them break down completely. This classical picture painted black holes as cosmic dead ends, places where information and energy vanish from the observable universe. Astronomers had begun detecting these objects through their gravitational effects on nearby stars and gas clouds, observing how matter would spiral inward, heating up to millions of degrees and emitting X-rays before disappearing forever, beyond the event horizon. The more massive the black hole, the stronger its gravitational pull, and the more efficiently it could consume everything in its vicinity. However, Hawking recognized that this purely classical approach ignored a crucial aspect of modern physics: quantum mechanics. At the subatomic level, the smooth fabric of space-time described by Einstein becomes a seething foam of virtual particle pairs, constantly appearing and annihilating in accordance with Heisenberg's uncertainty principle. These quantum fluctuations occur everywhere in space, even in what we consider to be a perfect vacuum. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. Hawking's breakthrough came from applying quantum field theory to the curved spacetime near a black hole's event horizon. He realized that the intense gravitational field would affect these virtual particle pairs in a profound way. Normally, virtual particles appear in pairs, one particle and its antiparticle, and quickly annihilate each other, returning their borrowed energy to the quantum vacuum. But near a black hole's event horizon, something extraordinary happens. The extreme curvature of spacetime can separate these particle pairs before they have a chance to annihilate. One particle might fall past the event horizon while its partner escapes to infinity. This process, Hawking discovered, would appear to distant observers as though the black hole itself were emitting radiation, a steady stream of particles carrying energy away from the black hole. This revelation was nothing short of revolutionary. If Hawking's calculations were correct, black holes weren't the perfect cosmic vacuum cleaners we had imagined. Instead, they were slowly evaporating, giving off energy in the form of thermal radiation. The implications were staggering. Black holes had a temperature. They could shrink, and given enough time, they might even disappear entirely. The radiation predicted by Hawking's theory would be incredibly faint for stellar mass black holes, far too weak to detect with current technology. A black hole with the mass of our Sun would have a temperature of only 60 billionths of a degree above absolute zero, making its Hawking radiation virtually impossible to observe against the cosmic microwave background. Yet this theoretical prediction would spark decades of intense research, debate, and discovery, fundamentally changing how we understand the relationship between gravity, quantum mechanics, and the ultimate fate of information in our universe. To understand how black holes could possibly emit light, we must venture into the strange realm of quantum mechanics, where the familiar rules of classical physics give way to probabilities, uncertainties, and phenomena that defy everyday intuition. At the heart of Hawking's discovery lies one of quantum mechanics' most counterintuitive principles: even empty space isn't truly empty. According to Heisenberg's uncertainty principle, energy and time cannot be simultaneously measured with perfect precision. This fundamental limitation allows the quantum vacuum to borrow energy for incredibly brief moments, creating pairs of virtual particles that spontaneously appear from nothing. These particle pairs consist of a particle and its antiparticle, an electron and positron, for example, which must annihilate each other within a time interval determined by the amount of energy borrowed. Under normal circumstances, these virtual particles live for such infinitesimally short periods that they have no observable effect on the macroscopic world. They appear, exist for perhaps 10 to the minus 21st seconds and vanish, returning their borrowed energy to the quantum vacuum. This process occurs countless times per second in every cubic centimeter of space, creating what physicists call zero-point fluctuations. However, the environment near a black hole's event horizon is far from normal. The extreme curvature of space-time, described by Einstein's field equations, dramatically alters how quantum fields behave. When virtual particle pairs appear near the event horizon, the intense gravitational gradient can separate them before they have time to reunite and annihilate. This separation occurs because the gravitational field varies significantly over very short distances near the event horizon, a phenomenon known as tidal effects. Hawking's mathematical analysis revealed that this particle separation process would result in one member of each pair falling into the black hole while the other escapes to infinity. The escaping particles would appear to distant observers as real radiation carrying energy away from the black hole. This transformation from virtual to real particles represents one of the most elegant examples of how quantum mechanics and general relativity interact in extreme environments. The temperature of this Hawking radiation depends inversely on the black hole's mass. More massive black holes have lower temperatures, while smaller black holes would be hotter. A black hole with the mass of our Sun would have a temperature of approximately 6.2 times 10 to the minus 8th Kelvin, colder than the cosmic microwave background radiation that fills the universe. Only primordial black holes with masses less than the Moon would have temperatures high enough to emit detectable radiation. This inverse relationship between mass and temperature leads to a fascinating consequence. As a black hole radiates energy and loses mass, its temperature increases, causing it to radiate even faster. This creates a runaway process where the evaporation rate accelerates as the black hole shrinks. For a solar mass black hole, this process would take approximately 10 to the 67th years, an incomprehensibly long time compared to the current age of the universe, which is only 13.8 billion years. The spectrum of Hawking. Radiation follows a perfect blackbody curve, identical to the thermal radiation emitted by any hot object. This connection between black holes and thermodynamics runs deeper than mere mathematical analogy. In 1972, Jacob Bekenstein had proposed that black holes possess entropy proportional to their surface area rather than their volume. Hawking's radiation provided the missing link, showing that black holes indeed behave like thermodynamic objects with well-defined temperature and entropy. The energy carried away by Hawking radiation must come from somewhere, and that somewhere is the black hole's mass energy itself. According to Einstein's famous equation E equals mc squared, mass and energy are equivalent, so as the black hole radiates energy, its mass decreases correspondingly. This mass loss causes the event horizon to shrink, reducing the black hole's surface area, and according to Bekenstein's formula, its entropy. This revelation created what became known as the information paradox, a fundamental conflict between quantum mechanics and general relativity that continues to challenge physicists today. The implications extend far beyond theoretical curiosity, touching on the deepest questions about the nature of space, time, and information in our universe. Hawking's discovery of black hole radiation opened a Pandora's box of theoretical challenges that continue to puzzle physicists nearly 50 years later. At the center of this intellectual storm lies what has become known as the black hole information paradox, a fundamental conflict between two of our most successful theories about the nature of reality. The paradox emerges from a basic principle of quantum mechanics. Information cannot be destroyed. In quantum theory, the complete description of any physical system is encoded in its quantum state, and the evolution of this state through time must be reversible, at least in principle. If you know the exact quantum state of a system at one moment, the laws of physics should allow you to determine its state at any other time, past or future. This principle, called unitarity, forms the foundation of quantum mechanics and has been verified in countless experiments. But black holes seem to violate this sacred rule. When matter falls past an event horizon, classical general relativity suggests that all information about its quantum state is lost forever, trapped beyond the point of no return. If Hawking radiation is truly thermal, meaning it carries no information about what fell into the black hole, then the evaporation process would permanently erase that information from the universe. This violation of unitarity would represent a fundamental breakdown of quantum mechanics in the presence of strong gravitational fields. The situation becomes even more complex when we consider the quantum entanglement between particles inside and outside the black hole. When virtual particle pairs separate at the event horizon, quantum mechanics demands that they remain entangled. Their properties remain mysteriously correlated regardless of the distance between them. The particle that escapes carries with it information about its partner's quantum state, creating a web of correlations that connects the black hole's interior to the external universe. This entanglement structure grows more intricate as the black hole evaporates. Each escaping particle becomes entangled with particles inside the black hole, while also being correlated with previously emitted Hawking radiation. As time progresses, the amount of entanglement reaches what physicists call the page time, the moment when roughly half of the black hole's initial entropy has been radiated away. At this point, the entanglement structure becomes maximally complex, and something dramatic must happen to preserve the quantum mechanical requirement of information conservation. One proposed resolution, known as the firewall paradox, suggests that violent quantum effects near the event horizon would create a wall of high-energy particles, a firewall that would incinerate anything attempting to cross the boundary. This solution preserves unitarity, but at the cost of violating the equivalence principle, a cornerstone of general relativity that states observers in free fall should not detect any local effects of gravity. Alternative theories have emerged to address these challenges. The holographic principle, developed from string theory research, proposes that all information contained within a volume of space can be encoded on its boundary. Applied to black holes, this suggests that information falling past the event horizon is actually encoded on the black hole's surface, accessible through careful analysis of the Hawking radiation's subtle correlations. The ADS-CFT correspondence, a powerful tool from string theory, provides another perspective. This mathematical framework establishes a precise relationship between gravity in the bulk of spacetime and quantum field theory on its boundary. Within this context, black hole evaporation can be understood as a purely quantum mechanical process that preserves information throughout, even though the mechanism remains hidden from observers using classical general relativity. Recent theoretical work has focused on understanding how information might escape through quantum error correction mechanisms built into the geometry of spacetime itself. These ideas suggest that the Hawking radiation, while appearing thermal to local observers, actually contains highly encoded information that could, in principle, be decoded to reconstruct everything that ever fell into the black hole. Experimental verification of these ideas remains far beyond current technological capabilities. The Hawking radiation from astrophysical black holes is too faint to detect, and the quantum correlations that might resolve the information paradox are even more subtle. However, analog systems in laboratory settings, such as acoustic black, holes in flowing fluids, or optical black holes in nonlinear media, provide testbeds for exploring these fundamental questions about the relationship between quantum mechanics, gravity, and information. While Hawking radiation represents one of theoretical physics' most elegant predictions, observing it directly presents extraordinary challenges that push the boundaries of what's technically possible. The faintness of this radiation for astrophysical black holes means that current detection methods fall short by many orders of magnitude. Yet creative approaches and emerging technologies offer hope for future observations. For a black hole formed from a collapsed star, typically containing 3 to 20 times the mass of our Sun, the temperature of Hawking radiation reaches only billionths of a degree above absolute zero. To put this in perspective, the cosmic microwave background radiation left over from the Big Bang has a temperature of 2.7 Kelvin, making it nearly 100 million times hotter than the Hawking radiation from a 10 solar mass black hole. Any attempt to detect this radiation would be overwhelmed by the background thermal noise from the rest of the universe. The situation improves dramatically for smaller black holes. The inverse relationship between mass and temperature means that primordial black holes, hypothetical objects formed in the early universe rather than from stellar collapse, could emit detectable radiation if they exist with sufficiently small masses. A primordial black hole with the mass of a large mountain would have a temperature of about 100 billion Kelvin and would evaporate completely in less than a second, releasing energy equivalent to millions of hydrogen bombs. Such explosive evaporation events would produce characteristic signatures across the electromagnetic spectrum, from gamma rays to radio waves. Current gamma-ray observatories like the Fermi Gamma-ray Space Telescope and the High-Energy Stereoscopic System, or HESS, actively search for these bursts. The absence of detected primordial black hole explosions places constraints on their abundance and provides indirect tests of Hawking's theory. Laboratory-based analog systems offer another avenue for studying Hawking-like radiation. These systems exploit mathematical similarities between the equations governing black holes and those describing other physical phenomena. Sonic black holes, created in flowing fluids where the flow speed exceeds the speed of sound, can trap acoustic waves just as gravitational black holes trap light. Similarly, optical black holes formed in nonlinear optical media can trap light pulses under specific conditions. Researchers have successfully created these analog black holes and observed radiation that shares key properties with Hawking radiation. While these systems don't involve actual gravity or space-time curvature, they provide valuable insights into the quantum field theory aspects of the Hawking effect. The Steinhauer group in Israel reported observations of correlated pairs of phonons, quantum sound waves, emerging from analog black holes, representing the closest laboratory analog to Hawking radiation achieved to date. Gravitational wave astronomy, revolutionized by the Laser Interferometer Gravitational Wave Observatory, or LIGO, opens new possibilities for studying black hole physics. When two black holes merge, they create ripples in spacetime that carry information about their masses, spins, and other properties. Future gravitational wave detectors with enhanced sensitivity might detect the subtle effects of Hawking radiation on these merger events, particularly for smaller black holes where the radiation is more significant. The proposed Laser Interferometer Space Antenna, or LISA, scheduled for launch in the 2030s, will observe gravitational waves from space with unprecedented sensitivity. This observatory might detect signals from intermediate mass black holes, objects between stellar mass and supermassive black holes, where Hawking radiation effects could be more pronounced. Additionally, LISA's ability to observe black hole mergers over much longer timescales might reveal subtle signatures of quantum gravitational effects. Next-generation space telescopes will also contribute to this search. The James Webb Space Telescope, or JWST, already in operation, can observe the infrared universe with extraordinary sensitivity. While it cannot detect Hawking radiation directly, it might observe the effects of evaporating primordial black holes on their surrounding environment, such as the heating of nearby gas clouds or the disruption of star formation processes. Theoretical work continues to refine predictions for observational signatures. Researchers calculate how Hawking radiation might interact with matter and magnetic fields around black holes, potentially creating detectable secondary effects. These interactions could amplify the signal or convert it to different wavelengths, making observation more feasible with existing or planned instruments. The search for Hawking radiation also motivates development of new detection technologies. Proposals for ultra-sensitive bolometers, quantum-limited amplifiers, and novel interferometric techniques could push detection thresholds closer to the predicted signal levels, while direct detection of Hawking radiation from stellar mass black holes remains beyond current capabilities. These technological advances bring us closer to this ultimate test of our understanding of quantum gravity. The process of black hole evaporation through Hawking radiation unfolds over timescales so vast they challenge human comprehension. Yet understanding this process reveals profound insights about the ultimate fate of our universe. As we peer into the deep future, black hole evaporation may represent the final chapter in the cosmic story, occurring long after stars have died and galaxies have dispersed into the cold darkness of an expanding universe. The evaporation timeline depends dramatically on a black hole's initial mass. A black hole containing the mass of our Sun would require approximately 10 to the 67th years to evaporate completely, a number so large that writing it out would require more digits than there are atoms in the observable universe. For comparison, the current age of the universe is merely 13.8 billion years, or about 10 to the 10th years. Even the most optimistic estimates for stellar evolution suggest that the last red dwarf stars will burn out in approximately 10 to the 14th years, leaving the universe in darkness long before any stellar mass black hole begins to shrink noticeably. Supermassive black holes, the giants found at the centers of galaxies with masses millions or billions of times that of the Sun, would persist even longer. The black hole at the center of our Milky Way galaxy, known as Sagittarius A star, contains approximately 4.3 million solar masses and would take roughly 10 to the 99th years to evaporate. Such timescales exceed even the proton decay time predicted by some grand unified theories, suggesting that black holes might be among the longest-lived objects in the universe. However, the evaporation process is not linear. As a black hole loses mass through Hawking radiation, its temperature increases inversely with its remaining mass. This creates a feedback effect where the radiation rate accelerates as the black hole shrinks. For most of its lifetime, a black hole loses mass imperceptibly slowly, but in its final moments, the evaporation becomes explosive and spectacular. During the last second of a black hole's existence, it releases energy equivalent to millions of nuclear weapons. This final burst produces particles across the entire spectrum: photons, electrons, positrons, neutrinos, and potentially exotic particles predicted by theories beyond the standard model. The exact nature of this explosion depends on fundamental physics we don't yet fully understand, particularly the unification of quantum mechanics and general relativity at the Planck scale. The end stages of black hole evaporation raise fascinating questions about information preservation. If the information paradox has a resolution that preserves quantum unitarity, then this final explosion must somehow encode and release all the information that ever fell into the black hole throughout its entire lifetime. The mechanism by which this might occur remains one of the deepest mysteries in theoretical physics. In the context of cosmological evolution, black hole evaporation represents a crucial phase in the universe's journey toward maximum entropy. Current cosmological models predict that our universe will continue expanding and cooling, eventually reaching a state called heat death, where all available energy has been converted to waste heat at uniform temperature. In this distant future, black holes would be the last sources of usable energy. The evaporation of black holes through Hawking radiation represents nature's final attempt to reach thermal equilibrium. As these objects slowly convert their mass into radiation, they redistribute energy throughout the expanding universe. The process is incredibly inefficient. For every unit of energy radiated away, vast amounts remain locked within the black hole's mass. Yet given enough time, even this inefficient process would eventually convert all matter into radiation. This scenario leads to what physicists call the Big Rip, or maximum entropy state, where the universe contains only isolated photons, electrons, positrons, and neutrinos at infinitesimally low temperature. The expansion of space would continue, diluting even this sparse matter and radiation until the average distance between particles becomes astronomical. In such a universe, the concept of time itself might lose meaning, as no physical processes would mark its passage. Some theories suggest alternative fates. If protons decay as predicted by certain grand unified theories, matter would disappear even before black holes finish evaporating. Conversely, if new physics prevents black hole evaporation or creates mechanisms for black hole formation in the far future, the universe might contain black holes indefinitely. The discovery of dark energy and the accelerating expansion of the universe adds another layer of complexity to these scenarios. Recent developments in string theory and quantum gravity suggest even more exotic possibilities. Some models propose that the evaporation of black holes might seed the formation of new universes through quantum tunneling processes, creating a multiverse where our cosmic death represents another universe's birth. While highly speculative, these ideas illustrate how the study of black hole evaporation connects to the deepest questions about the nature of existence itself. The 21st century has witnessed remarkable progress in understanding and experimentally probing Hawking radiation, transforming what was once pure theoretical speculation into an active area of experimental research. While direct detection of Hawking radiation from astrophysical black holes remains beyond current capabilities, ingenious laboratory experiments and theoretical advances have brought us closer to understanding this fundamental phenomenon. The most significant experimental breakthroughs have come from analog black hole systems, where researchers create conditions that mathematically mirror the physics of black hole horizons. Jeff Steinhauer's group at the Technion Institute in Israel made headlines in 2016 and 2019 by observing Hawking-like radiation in ultra-cold atomic gases. Their system uses a Bose-Einstein condensate, a quantum state of matter where atoms behave collectively, flowing at supersonic speeds to create an acoustic event horizon. In these experiments, sound waves cannot escape upstream against the supersonic flow, just as light cannot escape from within a black hole's event horizon. The researchers observed correlated pairs of phonons, quantum sound excitations emerging from the acoustic horizon. One phonon travels away from the horizon, while its entangled partner remains trapped upstream, perfectly analogous to the particle pairs predicted by Hawking's theory. Measurements confirmed the thermal spectrum characteristic of Hawking radiation, providing the first experimental verification of key aspects of the theory. Optical analogues have also yielded fascinating results. Researchers at the University of St. Andrews and other institutions have created optical black holes using nonlinear materials, where intense laser pulses modify the medium's refractive index. These systems can trap light pulses and emit optical analogues of Hawking radiation. While the physics differs from gravitational black holes, the mathematical structures underlying the radiation emission are remarkably similar. Theoretical progress has been equally impressive, particularly in resolving the information paradox that has puzzled physicists since Hawking's original work. The holographic principle, developed through string theory research, suggests that information falling into a black hole is encoded on its two-dimensional surface rather than in its three-dimensional volume. This radical idea implies that the universe might be fundamentally two-dimensional, with three-dimensional physics emerging as a kind of holographic projection. The ADS-CFT correspondence, discovered by Juan Maldacena in 1997, provides a concrete mathematical framework for understanding this holographic relationship. This duality establishes an exact correspondence between gravity in the bulk of spacetime and quantum field theory on its boundary. Within this framework, black hole evaporation can be understood as a purely quantum mechanical process that preserves information throughout, resolving the paradox through quantum error correction mechanisms built into spacetime geometry. Recent work by Ahmed Al-Mhairi, Donald Marolf, Joseph Polchinski, and James Sully revealed additional complexity in the form of the firewall paradox. Their analysis suggested that preserving information might require violent quantum effects at the event horizon, contradicting the smooth spacetime predicted by general relativity. This apparent contradiction has sparked intense research into the microscopic structure of black hole horizons and the nature of quantum spacetime. Quantum simulation represents another frontier in Hawking radiation research. Researchers use carefully controlled quantum systems, such as trapped ions, superconducting circuits, or optical lattices, to simulate the quantum field theory aspects of black hole physics. These simulations can explore parameter regimes impossible in natural systems and provide insights into the quantum information aspects of the evaporation process. The development of quantum computers opens new possibilities for studying these phenomena. Quantum algorithms designed to simulate curved spacetime effects and entanglement dynamics could provide unprecedented insights into the information paradox and the structure of quantum gravity. Several research groups are developing quantum circuits specifically designed to model black hole evaporation and test various proposed resolutions to the information paradox. Advances in gravitational wave astronomy have also contributed to black hole physics research. The precision measurements achieved by LIGO and Virgo collaborations provide detailed information about black hole properties and test general relativity in the strong field regime. Future upgrades and new detectors like the Einstein telescope will achieve even greater sensitivity, potentially detecting quantum gravitational effects or signatures of Hawking radiation in extreme black hole merger events. Machine learning and artificial intelligence are increasingly important tools in this research. Neural networks trained on large datasets of black hole simulations can identify subtle patterns and correlations that might reveal signatures of quantum gravitational effects. These computational approaches complement traditional analytical methods and help researchers explore complex scenarios that would be impossible to analyze by hand. The convergence of these experimental, theoretical, and computational approaches is creating an unprecedented opportunity to understand one of physics' most profound predictions. While direct detection of Hawking radiation from astrophysical black holes remains a distant goal, the combination of analog experiments, quantum simulations, and theoretical advances is steadily illuminating the deep connections between quantum mechanics, gravity, and information that lie at the heart of Hawking's discovery. Stephen Hawking's discovery of black hole radiation stands as one of the most profound insights in the history of physics, fundamentally altering our understanding of gravity, quantum mechanics, and the nature of spacetime itself. Nearly 50 years after its theoretical prediction, Hawking radiation continues to drive cutting-edge research and promises to reshape our comprehension of the universe's deepest mysteries. The impact of Hawking's work extends far beyond black hole physics. By demonstrating that black holes have temperature and entropy, he established deep connections between gravity, thermodynamics, and quantum mechanics that continue to influence theoretical development. The realization that black holes are thermodynamic objects with well-defined temperature and entropy led to the holographic principle, one of the most revolutionary ideas in modern physics, suggesting that the information content of any volume of space can be encoded on its boundary. This holographic insight has transformed our understanding of spacetime itself. Rather than being a fundamental arena where physics plays out, spacetime might emerge from more fundamental quantum information structures. This perspective has profound implications for quantum gravity theories, particularly string theory and loop quantum gravity, both of which attempt to reconcile general relativity with quantum mechanics at the smallest scales. The study of Hawking radiation has also catalyzed the development of quantum information theory in curved spacetime. Researchers now understand that the entanglement structure of quantum fields in gravitational environments follows precise mathematical rules that connect geometry to information. These insights have applications beyond black hole physics, influencing our understanding of quantum error correction, quantum computing architectures, and the fundamental limits of information processing in quantum systems. Quantum computing represents one area where Hawking radiation research has practical implications. The quantum error correction mechanisms that might resolve the information paradox share mathematical structures with quantum computing protocols, designed to protect quantum information from decoherence. Understanding how nature preserves information during black hole evaporation could inspire new approaches to building fault-tolerant quantum computers. The cosmological implications of Hawking radiation are equally profound. In the far future of our universe, black hole evaporation will represent the final phase of cosmic evolution, determining how the universe approaches its maximum entropy state. Understanding this process is crucial for predicting the ultimate fate of matter, energy, and information in our expanding cosmos. Some theoretical models even suggest that black hole evaporation might seed the formation of new universes, creating an eternal multiverse where cosmic death and birth are intimately connected. Hawking radiation research has also inspired new, experimental techniques and technologies. The development of analog black hole systems has advanced our understanding of quantum fluids, nonlinear optics, and quantum simulation methods. These techniques find applications in diverse fields, from superconductivity research to quantum metrology and precision measurement. The search for direct detection of Hawking radiation continues to push technological boundaries. Proposed detection schemes require advances in quantum-limited amplification, ultra-low noise measurement, and space-based observation platforms. While these technologies are developed for fundamental physics research, they often find applications in other fields, from medical imaging to telecommunications. Looking toward the future, several emerging research directions promise to deepen our understanding of Hawking radiation and its implications. Quantum gravity phenomenology seeks to identify observable signatures of quantum gravitational effects that might be detectable with next-generation experiments. The development of more sophisticated analog black hole systems could provide increasingly precise tests of Hawking's predictions and explorations of the information paradox. Advances in quantum simulation and quantum computing will enable detailed studies of black hole evaporation in regimes impossible to explore analytically. These computational approaches might reveal new aspects of the evaporation process and test proposed resolutions to the information paradox. The integration of machine learning and artificial intelligence with theoretical physics research is opening new avenues for discovering patterns and relationships in complex quantum gravitational systems. The philosophical implications of Hawking radiation research extend to fundamental questions about the nature of reality. The information paradox touches on deep issues about determinism, causality, and the relationship between physics and information. Resolving these questions might require new conceptual frameworks that transcend our current understanding of space, time, and matter. Stephen Hawking's legacy in discovering black hole radiation represents more than a single theoretical breakthrough. It exemplifies the power of human curiosity and mathematical insight to reveal hidden truths about the universe. His work demonstrated that even the most extreme objects in the cosmos are governed by the same fundamental principles that operate in earthly laboratories, unifying our understanding of phenomena across vastly different scales. As we continue to explore the implications of Hawking radiation, we honor not only Hawking's memory, but also the broader tradition of scientific inquiry that seeks to understand our place in the cosmos. The questions raised by his discovery continue to challenge and inspire new generations of physicists, ensuring that the exploration of these cosmic mysteries will remain at the forefront of human intellectual achievement for decades to come. Through analog experiments, theoretical advances, and technological innovation, we inch closer to fully understanding the profound implications of Hawking's insight that black holes are not the cosmic dead ends we once imagined, but rather fascinating laboratories where the deepest laws of nature reveal themselves through the gentle whisper of quantum radiation emerging from the darkness.